In this video I want to talk about Boolean equations. So if you remember from before when I talked about basic logic gates, you saw that one of the representations that we had for any logic gate was a Boolean equation representation. But of course that was for a very simple logic gate. What about if we have a more complex logic circuit? So here you will learn how we can drive Boolean equations for more complex logic circuits. So Boolean equations describe the functional specification of outputs in terms of the inputs for any logic circuit. So it doesn't matter if the logic circuit is combinational or sequential. So generally speaking, Boolean equations are applied to both of them. Of course, the way to drive them are different, but nonetheless Boolean equations describe the functional specifications of any logic function. So let's just take a look at one example here. So this is what is being called as a 1-bit full adder. So the way this circuit works generally, of course in later lectures I will go through them in much more detail. We have one bit of input called A, another bit of input called B, and the third one is C in, or the carry that is from the previous state. We have the carry out, and we have the summation result. So when you add two binary number, let's just create a random one here, 0 0 1 1. So when you add these two together, if you remember from before, we added 1 plus 1, the result was 1 0, so we had 0 here. We had 1 carry to the next stage. Now we had 1 plus 0 plus 1, the result is again 1 0, so we have 0 here. We have 1 carry to the next stage. We have 1 plus 1 plus 0, again the result is 1 0 0, and then 1 carry. So let me just specify this. And finally we had 1 plus 1 plus 0, which is again 1 0, so we have 0 here, 1 carry, and then this one completely comes down. So as you can see here, when I add these two binary numbers together, I do it in 4 stages, right? I do it bit by bit. So this circuit here basically does one step of this process. So as you can see, here we have the carry in from the previous state, we have bit A, and then we have bit B, and then we calculate the summation, and then we calculate the C out that goes to the next state. So basically this circuit is trying to find out what is the functional specification of this 1-bit full adder. So if we have this truth table, and if I provide all the possible combinations, again I'm here counting from 0 to 7, right? Because we have 3 inputs, we have 2 to the power 3 or 8 possible combinations that range from 0 to 7. 0 1 1 1 0 0 1 0 1 1 1 0, and finally 1 1 1. Based of each one of these combinations, we have either a carry or a value for the summation. So 0 plus 0 plus 0, the output is 0, and the carry is also 0. 0 plus 0 plus 1, the carry is 0, the summation is 1. The same is true for this one as well. when we are adding 0 plus 1 plus 1, the carry is 1, the summation is 0. So you see these two combined create 1, 0. Then for the next one, again it's going to be 0, 1. For the next one is 1, 0. Again 1, 0. And finally we have 1, 1, because when we add 3 ones together, the result is 3, which is in Boolean it is represented as 1, 1. So now we have created this truth table. But to implement this function, having only the truth table is not enough. We need to have Boolean equations that specify what this function does. So how we can get from this truth table to these two equations that represent the relationship between S and C out with the inputs A, B, and C in? That's the question that I want to answer here. So before I answer that question, let's just go through some definitions. So the first definition that we have is the definition of a complement, which is a variable with a bar over it. So this is something that you have seen So before I answer that question, let's just go through some definitions. So the first definition is the definition of complement, which is a variable with a bar over it. You have seen this before. This is equivalent to having a variable that goes through a NOT gate. The next definition is the definition of a literal, in which we have either a variable or its complement. So any variable or its complement is called a literal. Then we have the definition of implicant, which is a product of literals that we can have. So for example, here we have A, B, C bar. So if you remember from before, this is basically A and B and C bar. The next one is A bar C. The next one is B C. Again, these are ANDs that we can have. So this is what is called an implicant. Then we have minterm, which is the product or AND of all the variables that we have for a specific function. So if we are trying to find out what is the relationship between outputs and 3 inputs, a minterm is going to be a product that contains all the variables. So A, B, and C. Of course, here we have C bar, but it is variable C nonetheless, right? It is the complement of variable C. And this is what is different between a minterm and an implicant. For the implicant, it wasn't necessary to have all the variables in the product. But for the minterm, we must have all the variables in the product. Let's say if we have 4 variables, 4 input variables, in that case, an example minterm could be A, B bar, C, D bar, for example, right? So this is a valid minterm for a 4 variable circuit. And then finally we have the definition of max term, which is a sum or an OR that includes all input variables again. So when you compare it with min term, the similarity between a max term and min term is that they both contain all the input variables. The difference is that in min term we calculate the product, in max term we calculate the sum or of all the variables or their complements. So now that we saw these initial definitions, let's just go through the first method that we want to use to go from a truth table to a Boolean equation. This is what is called a sum of product or SOP form. So all the equations, all the Boolean equation can be written in SOP form. To do that, we have to consider that each row in the truth table has a unique min term associated with it. So let's just take a look at this two input example. We have A and B as the two inputs. We have Y as the single output. And I have extended this table to include the min term and the min term name as well. Of course, in practice, we don't usually do this. If you want, you can do it, but it is not necessary. Just by having all the inputs and outputs, basically the combination of all the inputs, you basically implying the different min term that you have. So as you remember from before, a min term was a product of some literals, right? Whether the variable itself or its complement. But it was necessary that you have all the variables. So as I said, the min term is unique for every row of the truth table. Why is that? Because each min term is true only for that specific row. So let's just see how this thing works. We have, for the first row, we have A to be 0 and also B is 0. We say that the min term associated with this row is A bar multiplied by B bar, or A bar and B bar. We say that this min term is only true for this row. This is easily verifiable. AND of A bar and B bar is only 1 when A is 0 and B is 0. So let me just add some more columns to this table. And for these columns, I put the min terms. So we have A bar, B bar, we have A bar B, we have AB bar, and then finally we have AB. So again, consider that each one of these is the AND of these two variables. So if I have A to be 0 and B to be 0, then A bar is going to be 1 for A bar is going to be 1 for the first row. B bar is going to be 1 again for this first row, and AND of 1 and 1 is going to be 1. Recall from the definition of the basic AND gate that we had. But what about for the rest of these? A bar B is going to be 0. Why? Because even though A bar is 1, B is 0 for this specific row. So the AND of 1 and 0 is going to be 0. The same is true for this one and this one as well. So at least one of them is going to be 0, either A or B, or like A bar or B bar for these three, which makes the value for these three min terms to be 0. We can do the same for the second one as well. So when A is 0 and B is 1, we say that the associated min term for this row is A bar B. So in this case, A bar B bar is going to be 0. Why? Because when A is 0, A bar is 1, but when B is 1, B bar is going to be 0. So the AND of 1 and 0 is 0. But on the other hand, the value for A bar B is going to be 1. Because when A is 0, A bar is 1. When B is 1, here we have B itself. So we have 1 and 1, which is going to be 1. And the same thing would apply to the rest of them. So if I fill out this whole table, what I get is something like this: 0, 0, 0, and finally 1. As you can see, each one of these minterms is only true for one row, right? So this one is only true for the first row, this one is only true for the second row, for the third row, and finally for the fourth row. So that's why I say each one of these minterms is unique for a specific row. So again, each minterm is true for one row and one row only. So now that we have this, so up until now we didn't care about the output. But now that we have these things figured out, we can form the Boolean equation for output by ORing the minterms for which the output is true. So the output is true when A is 0, B is 1, and also it is true when A is 1 and B is 1. Since that is the case, Y is basically the result of ORing the minterm associated with this row, with the second row, and the minterm associated with the fourth row. So we have Y to be equal to A bar B plus A B. Or if you want to use the minterm names, it's going to be M1 plus M3. Or a shorthand version is to use the summation sign, which you have probably seen it in mathematics, that basically lists all the minterms. So all of these representations are equivalent, so it doesn't matter which one you use. Of course, for these two, it is important that you have all your rows in order, right? Again, you see here, this is equivalent to 0, this is equivalent to 1, this is equivalent to 2, and this one is equivalent to 3. If you have all of them in order, in that case, using the minterm names makes sense. If they are not in order, it's always best to use the minterms themselves. So how you can create these minterms? It is easy. Let me just erase this. So to find out the associated minterm for each one of these rows, take a look at the variables for each one of these rows. If the variable is 0 for that specific row, in its minterm we have the variable with a bar. If the variable is 1, we have the variable itself. So for example, for this row, to get the minterm, since A is 0, we have A with a bar, so the complement of A. For B, it is the same. B is 0, so we consider B with a bar. So this will be the associated minterm. Of course, for a 2-input case, this can be more obvious, but to avoid writing all the minterms all the time, this is a good shorthand solution. So anytime that you see a variable with 0, you use its complement. Anytime you see a variable with 1, you use the variable itself. So this is the mean term associated with the second row. For the third row, we have a itself because the value of a is 1. B has a bar because the value for b is 0. And finally, for the last row, we have a b. And that is why we call this the sum of product, because we are ORing some products. So again, a quick overview. We create the truth table for our function first. For each one of these rows, we have a unique mean term for which the mean term is true for that specific row. To create the function, we OR all the mean terms for which the output is true. So here we have these two rows for which the output is true. We basically add the two mean terms for these two rows. And then these are the two additional representations that are basically equivalent. So that was how we can create a sum of product form of a Boolean equation. Now let's just take a look at a product of sum, or POS, form of the Boolean equation. Again, all Boolean functions can be represented or written in POS form. Each row has a max term associated with it. And a max term, if you remember from before, was a sum or OR of all the variables, whether the variables themselves or their complement. One thing that is different for max term as opposed to min term is that for min terms, the min term was true only for that specific row. For max term, the max term is false for that specific row. It is true anywhere else. So let's just do the same here too. Let me just extend this table to include all the max terms. So we have a plus b bar, a bar plus b, and finally a bar plus b bar. So as I said, each max term is false for that specific row and only that row. Let's just see how it works. For the first row, we have a and b to be both 0, and we say that the max term associated with this row is a plus b, or a or b, right? So what is the value of a plus b when a and b are both 0? So 0 plus 0, it is 0. Or more accurately, 0 or 0 is 0. What is the value of a plus b bar when a and b are 0? So in this case, a is going to be 0, but b is 0, which means that b bar is 1. So 0 plus 1, it is going to be 1. The same analogy can be applied to a bar plus b, because when a is 0, a bar is 1. So 1 plus 0 is going to be 1. And finally for this one too. If you repeat this process for all these rows, this is what you get. So here we have 1, here we have 0, we have 1, we have 1, then we have 1 here, 1, 0, and 1, and then finally we have 1, 1, 1, and then 0. So as you can see, each one of these minterms is only false for one specific row, and only that row. So in a sense, each max term is unique for one specific row. In mean terms, the mean term was only true for one specific row and only that row. For max terms, the max term is false for one specific row and only that row. So now that we have this, we can form the function by ANDing the max terms for which the output is false. So we look for the rows for which the output is false. And then what we do is that we AND the max terms that associate with those rows. So for example, for this function, the output is 0 for the first row and the third row. We find the max term and we AND those max terms together. And that is how we create the function in a product of sum form. One thing that you probably noticed is that everything is completely opposite from the sum of product form. So first of all, in sum of product form, the mean terms were true for one specific row. Here, the max terms are false for one specific row. In sum of product form, you were looking for rows for which the output is 1. In product of sum form, you are looking for rows for which the output is 0. In sum of product form, you summed or ORed all the mean terms for which the output is 1. In product of sum form, you AND or you multiply all the max terms for which the output is false. So as you can see, everything is opposite. Now, what is the shorthand way to create these max terms in order to not write them all down? So for example, if you have a function that has 4 inputs, you don't want to write all the max terms for all the 16 rows that you have for the truth table. So the way to do it is doing it like this. Anytime that you have a variable to be 0, for the associated max term, the variable itself appears. So here we have a to be 0, b to be 0, which means that the max term associated with this is going to be a plus b. Anytime you see a variable being 1, then you consider its complement. So a is 0, so we consider the variable itself. B is 1, so we have a plus b bar. You apply the same analogy here. You have a bar plus b. And finally the last one, which will be a bar plus b bar, because both a and b are 1. Of course, I don't expect you to memorize all of this right away, but you should practice. You should practice, you should create truth tables with different number of inputs, and for each one of them go through all these steps one by one, so you can easily then identify whether you have to create all the max terms or only a few of them. The same is true for the mean terms as well. So it needs to you need to keep practicing until you are able to do all of these much easier. Similar to the sum of product form, which we had the shorthand version, here we use the generic symbol for product, and then we mention the number of the max terms that we use, basically the index number. So here we have max term 0 and max term 2. Of course, this only works if you have all your rows in order. If they are not in order, then this one is better, right, and less confusing. So now that we saw this, let's just take a look at one example. So you are going to the cafeteria of the university for lunch, but there are some conditions. You won't eat lunch. Basically, E considering is used to represent eating lunch. So you won't eat lunch. That means that E bar is true. If it's not open, so if O bar is the case, or if they only serve corn dogs. So we have two inputs. One is the cafeteria being open or not. We show it as O. And the other one is C, which signifies whether they only serve corn dogs or not. So based on this, we want to determine the outcome of this example. So if it's not open, you don't eat lunch. Basically, anytime that O bar is true, basically O is 0 or O bar is 1, you won't eat lunch. So that means that when O is 0, E is 0. The same is true for the next row as well. But now let's say the cafeteria is open, so O is 1. But they only serve corn dogs, so C is also 1. So the last row, basically, you don't eat lunch either. But if the cafeteria is open and they don't only serve corn dogs, then you eat. So this will be the truth table that you have for this example. Now based on this, let me just repeat this here. 1 0 0 0 1 0. We want to find out the Boolean equation for this truth table based on sum of product or product of some form. So remember, for the sum of product, each row had a unique mean term associated with it, which was only true for that specific row. To get the function in sum of product form, you had to find all the rows for which the output was 1, and then you had to write the function by ORing all those mean terms for which the output is 1. So here there is only one row for which the output is 1. So that means that the function is going to be only containing one mean term. So the mean term here is O C bar. So again, as you can see here, whenever we have the variable as 1, we consider the variable itself. Whenever the variable is 0, we consider its complement, right? So that's when you don't want to write all the mean terms. For the product of sum form, we had a similar analogy, but now everything was completely the opposite. So we were looking for rows for which the output was 0. So we have 3 rows in this table for which the output is 0. We said that there is a unique max term associated with each row, right? That max term is only false for that specific row and only that row, right? So it's true everywhere else for every other row, but it is false for that specific row. To write the function in terms of product of sum or product of max terms, we add all the max terms for which the output is 0. So we have 3 max terms here for which the output is 0. We have O plus plus C We multiply that or AND that with O plus C bar. We AND that with O bar plus C bar. Again, anytime you have a variable with value 0, you consider the variable itself. Anytime you have a variable with value being 1, with its value being 1, you consider its complement to create the associated max term for that specific row. So this is how we can come up with the two forms of this function, one based on sum of product form and the other one based on product of sum form. So as you can see, these two functions are equal even though they are written completely differently. So one seems to be much smaller, much shorter. The other one is much more complex, right? But either of them are representing the exact same function, right? So they are equal. So depending on the problem that you have, you might choose the sum of product form or the product of sum form, right? Because one of them can give you a simpler form for the Boolean equation. So in this video, we learned the basics of Boolean equation. We talked about min terms and max terms and how they are very useful in helping us to come up with Boolean equations for specific functions. So we saw sum of product form or product of sum form. So just by knowing how to use sum of product or product of sum form, you are able to write whatever logic or Boolean equation that you want. If you have the truth table, you can come up with the Boolean equation, and it doesn't matter if the function has 1 input, 2 inputs, 3 inputs, or a billion inputs, right? So the rules that we described here are true in general, right? So pay close attention to these two forms and practice so you can master them.